Good morning. I'm going to present for you some of the results from the baseline project. It's called Baseline Proposal on Sampling Plans for Seafood to Address Selected Safety Criteria. And I'm going to present for you here the results we have for Listeria monocytogenes in salmon and salmon products, about Vibrio in shellfish, and about mercury in tuna. First, the role of the baseline project. It is to suggest performance objectives and fit-for-purpose sampling plans for some of these criteria. And in detail, that means that we are going to assist the translation from food safety objectives put down in the legislation over to performance objective on the operative level in industry and on retail level. We are also going to set up sampling schemes and fit-for-purpose sampling plans for detect of non-complying or non-conformance lots or batches. And when needed, we are have also suggested alternative or new analysis methods when needed. First, I'm going to talk about the Listeria criteria. They are very well described in the legislation for ready-to-eat foods. You can see them here, and it's from the microbial criteria in the food law, and which I suppose you know very well. And they describe how, which levels of Listeria that is allowed to have in the ready-to-eat foods. And it describes the category of the products depending on the growth potential. If you have a product able to where Listeria can grow, then you have different criteria from if it is not able to grow. Then you have a sampling plan. Usually it is 5 samples to take. None of them should be above the detection level. And the limit value should not exceed 100 CFU per grams on the last day of shelf life. If the product can grow and you cannot prove that the level is not going to exceed 100 CFU per grams, you have to prove absence. And then it's indicating an analytical method to use. That's the ISO method for qualitative and quantitative detection, indicating a detection level. And then the sampling time, usually the last day of shelf life or at the other level. So then, while this is so well described, do we need more? And that we wanted to challenge that in our project. And we think we need more than this legislation. Because the fish, the salmon, the sea bass, tuna, it is going to be used for several products. Like what you see here, the normal fresh, chilled, gutted cutlets, the fillets. It's sometimes used for sushi. It is sometimes used for cold smoked salmon. It is sometimes used in other products as well, like surimi. Not salmon so much, but the others. And then the question is, when the maximum level allowed to have is 100 CFU per grams around here on the last day of shelf life, what can it be? What can the level be on the fresh fish level? To ensure that the level is not exceeding 100 CFU per grams on the last day of shelf life. We were lucky in our project because we got access to a company that had been struggling with Listeria in their facilities for years, but had managed to keep the levels very, very low. Anyway, we were allowed to take samples from them, and we analyzed the level in many different batches, and we stored the samples for a week or for 2 weeks, sometimes at abuse conditions, and then we measured the level again. And we saw interesting things. Ideally, you could hope that the level was always below 1 per CFU per gram, 1 per 25 gram. That means not detected in 25 grams. But when we analyzed these samples, we used 1 per sampling point. On the first day, this is the results for 1 day, one of the batches only, actually the worst one in terms of listeria levels. We saw that 3 of the samples, they were negative. 7 of them, 7 of them, they were detectable in qualitative analysis, but not in quantitative. That means that all of them had less than 10 CFU per grams. Then we stored the samples and took new samples for 1 week for 4 degrees and stored the fish for 4 degrees. Then we saw there had been a significant growth. Actually, then 1 of the samples, or 2 of the samples, had already exceeded 100 CFU per grams. 7 of the samples were now between 10 and 100 CFU per grams, which means acceptable to eat. This is not longer according to the law. And then the last sample, it was still negative. Then we stored the fish for another week at 4 degrees. And then it was still 1 down here, but the others, they were all above 100 CFU per grams. We did also another version where we stored the fish at abuse temperature. And in this case, all of them exceeded the acceptable level. So we could see a significant growth in the salmon. Even though at the beginning, as you remember, none of them were detected in all samples had less than 10 CFU per grams from the beginning. Still, the levels could grow this high. We did the same analysis for many different batches, as I said. And we had got help from statisticians to estimate the distribution. That is what you can see here. And you see on the first day, the distribution and the levels. You can see up here the cumulative levels. Here, the median value was actually around 1 per 4 gram. 1 listeria per 4 gram. Then you can see an increase over time and an increased distribution. So then how can we calculate how much listeria the fish can contain at the very beginning, at the production level, day, when the level at the end of shelf life should not be higher than 100 CFU per gram? Well, I guess you know that bacteria, they multiply 2 by 2. That means 1, 2, 4, 8, 16, 32, 64, 128, and so on. So what we can do is to calculate back, going back from 100 down to 1 doubling time back is 50, 1 more is 25, 12.5, 6.25, 3.13, and so you can go on. We have seen in our experiments that when we do challenge studies, the doubling time for each doubling is around 1.6 days. In naturally contaminated samples, the doubling time is a little longer. That means that if you in 2 weeks need, for 2 weeks of storage, you have room for around 9 doubling times. Okay? How much, around 7 doubling times. Then how much can you accept to have? If you go 7 doubling times down, you can go to 1 to 2 CFU per grams. If you have that and you store the fish at 4 degrees, then you will not exceed 100 CFU per grams by the end of shelf life. So we have used this, the data from the naturally contaminated samples, the simulations we've done, and some more of the experiments, and then we have estimated that depending on the intended use and on the storage time, the storage temperature, we have calculated these performance objective estimates at the day of production. If you are going to store the fish on ice all the time, you don't need to consider growth so much because the growth at that time is next to nothing. You can, by production, tolerate this level. It's our opinion, based on the results we've done. If you are going to label your products with 1 week shelf life, 4 degrees Celsius storage time, you can accept more or less this level. If you're going to claim 2 weeks shelf life, you have to go down to this level. And if you have to take into account that there will be abuse temperature, you cannot tolerate anything. You have to prove absence in 25 gram. So this is our suggestions. Well, salmon is used for several products, for instance, sushi. So then what happens? If you use the fish that had this high level, or this high level, and you produce sushi of it. Or if you use fish from having less than 10, well, how far up can you go if you're going to produce sushi of your fish? Sushi, it's produced in a, you could put it easy this way. It is salmon or any other fish or any other shrimp or any other vegetable that you put together with marinated, acid marinated rice. Okay. Then you put them together, and in pre-packed trays, like you see up there, the shelf life is up to 3 days. At least that is what we have seen. After the sushi is prepared, it's transported to the home or where you're going to eat it, and then it should be stored at room temperature to develop the flavor. So the taste will be optimal. And what will the levels be then? We carried out a challenge study where we used the ordinary fish, which is then the sashimi, and then we inoculated the fish that we're going to use for sushi, sometimes on the side towards the sushi and sometimes on the side away from the sushi. Then we saw interesting things. In the sashimi, that means in the fresh fish, you see the yellow line, we had a growth. It's the upper one. For the sushi, however, especially in the case when the listeria were pointing against towards the acid marinated rice, there was hardly any growth at all, as you can see on this red line. During the tempering period at room temperature, then, in case of the fresh fish, it was a 1 log increase only in this period, just taking for a few hours. It's the dots you can see above. But in case of sushi, there was the growth during this tempering period, it was much, much lower. So then, we went back to the calculations to see how high can the levels be in the salmon before you produce it to sushi. Sorry. And we realized it didn't need to be so much lower than for the fresh fish, unless you were going to use it for sashimi, because the preserving effect of the acid in the rice. So, do salmon need to be listeria-free to make sushi safe? We asked. And we answered ourselves, no, it doesn't have to. But the levels have to be very low, far below 10 CFU per grams, which is the detection level today in the reference method. And the levels have to be that low in the entire batch. So then what about smoked salmon? Do they have a different pattern? Well, we saw there a very, very limited growth. If there is growth, significant growth in cold smoked salmon, it's usually due to uneven distribution of salt and smoke compounds. So the pattern is not very different there. Then the next question is, how can we do a sampling plan? How can we do the sampling so to make sure that the levels will be sufficiently low in the whole lot, whole batch? Actually, we first wanted to know, is Listeria evenly distributed in the batch, or is it likely to be clusters somewhere? And the first thing we did, take away these things. The first experiment we did, it was to be pieces beside each other like this. Then we inoculated the one in the middle, only one. And then we put the package into the right storage temperature, and then we analyzed each and single piece in parallel experiments after 3 days and after 7 days. And we were a little surprised to see that after 3 days there were only traces here. This was inoculated piece. And after 7 days, still it was only this part that was contaminated. While this, they were more or less, they were listeria-free. So we concluded that the contamination, it remains local, but you have high growth in some of the pieces. Okay. This was as long as the fish was stored cold. If we put ice on it, the ice between the foil and the fish, we had listeria everywhere. So the water from the melting water from the ice, it was a transport medium for the bacteria. That was in this direction. What about the vertical direction? Then we did what you can see here. We packed the fish in a pile in a little bit more advanced boxes than here, but again, then we inoculated the piece in the middle. And what we saw was that the listeria, it spread downwards and to the side. And here was the main, all pieces here were always positive. So there is some kind of clustering. We used these results to develop a sampling method, where we put pieces like this and took as much as 100 grams of fish, not 25 grams as the original one, but we used 100 grams of sample. And then we found that if we were washing it with a broth, this is water, but assume that it is a broth, then we could collect all the listeria from the fish. And then what we could do to quantify, it was to use an MPN method like this. MPN, that means that here we could seal, we could fill the liquid, the washing liquid, in here. We could seal it. I can't do here, but the principle is here. And then we could estimate and measure some of the wells in the lab and see how many positive and how many negative wells. That gives an option for give an accurate enumeration, and we obtained a detection level of 1 CFU per 5 grams of fish. That means that we have obtained an analytical method that is sufficiently good to ensure the food safety, even if the PO is 2 CFU per grams, or even lower. It's also another way of doing sampling in an easy way. You can use pooled sampling. In this case, it is used for cold smoked salmon. 6 samples taken, 4 individual samples are taken, and then they are enriched, each of them, then put together, and you can measure in only one plate. If you are going to analyze a non-complying lot of cold smoked salmon, well, actually there shouldn't be any, then this is a sufficiently good method to do so. It's easy, it is on a whole lot level, it is sufficiently accurate. So it's an easy way. So the systematic variations we've seen is that, I haven't shown these results now, but we can say that the morning samples, they were different from the late day samples. In this case, in this company that we studied, the morning samples had higher prevalence and higher levels. In other companies, it may be opposite. We have seen that the local contamination, as we did, it usually remains local. That means that if Listeria spreads, it goes mainly downwards. Listeria is usually brand related because of house strains. So to do sampling on the retail level and believe that you have a representative sampling to look at single companies, single facilities, that will not be the case. And the opposite, if you analyze samples from one company, you cannot assume that you have a picture of the whole, of all kind of fish on the market. So then coming back to, do we really need more? Yes, we have seen that we need more. Well, the categories of the ready-to-eat foods, they're okay. We see no need for change there. Well, I should say that if you're going to use performance objectives, then you have to use, then there is need of changes. Well, in our experiments, it seems that a sampling plan to look at a non-complying lot, then you may need 6 or 7 products, samples, depending on the purpose and depending on the product. The limit values, again, this is when the sampling is carried out not on the last day of shelf life, but earlier. And there is a growth potential in your product. Then we agree that in some cases you need to prove absence, but in many cases, then 10, 2 or 5 are okay. You can look at the table again, as I showed some minutes ago. Well, the analytical method, the detection level in the present analytical method, it is 10 CFU per grams. Before the performance objective can be implemented, analytical methods with detection level 2 CFU per grams or even lower is needed. And as I hopefully have showed you, we have some prototypes of these methods now after baseline. And then the sampling time, it has to be before the last day of shelf life. So to implement performance objective, or you cannot use the criteria in the food law, but you have to translate them like we have done here. That was it for Listeria. Then we go to Vibrio in shellfish. I will not say very much about it, but Vibrio parahemolyticus, that is a pathogenic strain. It carries some toxicity markers. And in our project, we have sampled shellfish from some areas in Italy. And we have been looking both for parahemolyticus in general and for this bacterium with the pathogenicity markers. There are the results. I will not go into details, but I can draw the conclusion. The prevalence of parahemolyticus is around 14%, but the prevalence of toxigenic markers is around 2.4. That means that all parahemolyticus do not carry pathogenicity markers and are therefore not leading to illness. So therefore, we are suggesting two ways to handle this in order to not waste shellfish unless it's necessary. We have seen that the pathogenic Vibrio parahemolyticus, it is usually not found unless the level is above 1,000 CFU per grams. So that means that it is, we speculate a little and believe that if the shellfish contains less than 1,000 Vibrio parahemolyticus per grams, it's probably safe because then it's not likely that there will be pathogenicity markers. In the other conclusion is that in this region with a high prevalence, it is most likely that it will be more useful to develop safety criteria based on pathogenicity markers than on Vibrio in general. Well, these were studies carried out in Italy and in Croatia. And here we have the European dimension, because if we had done the same thing in Norway, it is so cold in the water there that there is hardly any, I think it has been detected pathogenic Vibrio only a few times, maybe even a couple of times. So with these circles I want to illustrate the different approaches that can be used in the different countries. If you take Italy here as an example of where there is a high prevalence, it really makes a difference if you go for Vibrio in general, the blue circle, or you go for the Vibrio in pathogenicity markers. Because if you go for the Vibrio species in general, you will waste a lot of shellfish that is actually safe to eat. But in Norway and other places where you have a very low prevalence, it doesn't matter if you measure Vibrio species or the pathogenicity markers, because the loss will be so small anyway. So it's not always, we believe it's not always relevant to go for the same criteria everywhere. Then I go to the mercury in tuna. Mercury, it accumulates from the food the tuna is eating. There are a lot of different species. There have been developed guidelines about or regulations about what the acceptable levels are. So then the challenge is to verify the level. And the analysis, they are relatively expensive. So the best way would be then to do it as cheap as possible without getting the risk as low as possible. And the University of Brest, they have done several simulations based on a lot of literature data, and they have compared the likelihood of overestimating and underestimating the level based on if you use only one sample, two tunas, 5 tunas, 10 tunas, or one pool of 2 tunas, and so on. They have used a term called producer risk and consumer risk. Producer risk, that means that is high if the level is underestimated without reason. Oh, sorry, if it's overestimated, that means that the analyst is giving a too high level compared to what the level really is. While on the consumer risk, if they have to carry the uncertainty of the sampling, that means that they get a higher likelihood of being poisoned because the analytical method or the sampling plan is underestimating the levels. The best trade-off is when the producers and the consumers carry the same risk. And based on that, our colleagues in Brest, they are suggesting that one pool of 10 tunas, that is the best trade-off. Other people have concluded differently. And the reason why is probably that they have set up other rejection criteria and acceptance criteria. Still, this method that has been used can be used to develop sampling plans depending on the safety margin you are going to do. Since mercury is accumulating in tuna based from the feed, it means that the larger, the older the tuna grow, the higher is the levels of mercury compounds. So it has also been done a study where you can see, is it enough just to look at the size or the body weight of the tuna? And then from there you can calculate what the mercury level will be. And in many cases it is possible. Here we have given results for 4 species of tuna. In case of skipjack tuna, it seems that the level will never be so high that it will exceed the levels, acceptable levels. For the other ones, it seems that it can be put a threshold weight where you should not longer eat the tuna to be sure that you will not, at least not if you eat a lot of it, to make sure that you will not exceed the acceptable level. I have not had the time at this presentation to go into all details and all parts of our studies, but if you found this interesting or would like to see if there are more relevant things to be done, I recommend that you go to our website and download our deliverables. There are reports open for everyone, and you can get more results there. Thank you for your attention.